Okay, so thank you. So today I'm going to talk about pseudorandom quantum states with proof of destruction. It's a joint work with Vika Bikoski, or Satat, and Om Zishmaeli. Too loud? Yeah, this one. Okay. Is it fine? Yeah, I think this. Yeah, I think it's better. Okay, I'm back. Okay, so I'm going to start with a very quick recap of these pseudorandom quantum states that we already saw multiple times today. So I'm going to borrow a few slides from the tutorial today. Okay, so what are pseudorandom quantum states? Again, they are just family of quantum states, one for each key in 0,1 per lambda. And this can be efficiently generated using pseudorandom PRS generator G. So for G outputs n qubit pure state for every key k, and the indistinguishability basically says pseudorandomness is that for every t, no polytime distinguisher can distinguish between t copies of a state sampled from this family or a truly hard random state, right? Okay. And again, this is different from the concept of state t designs because that only works for some fixed t, but in case we want it for arbitrary polynomial t. Okay. We also saw pseudorandom function like states, where now the generator also takes an input x from the input space. And now the indistinguishability, we need that for any set of points x1 till xs, these t copies of psi1 till psi s will be indistinguishable from t copies of mu1 to mu s, where psi1s are basically generated by the generator on x xi's, and the mu i's are generated by just sampled from the independently from the Haar measure. And it's important that this distinguisher can actually choose these x1 till x's, right? Okay, so this we already saw. Let's move to the other part of the title, which is quantum states with proof of destruction. Okay, okay. So imagine the following setting, that Alice has something precious, let's say some money. So in this case, you can think of Alice as a bank who mints, who mints basically a money state using some secret key that she has, and then sends to Bob. Now, Bob, after a while, he says like, I would like to trade this money state that I have for an ice cream popsicle from you to Alice. And then Alice says, sure, I'll give you that, but you must then destroy your money state. So can you destroy it? And now the question is, how can Alice verify that Bob actually destroyed it? So if this precious state sigma was classical, if this money is classical, then there's no hope. You can just copy it and keep it to yourself. So Bob has a copy, so even if he discards, it doesn't really make sense to talk about destruction here. But if sigma is quantum, then this is not true in general. We know that. And now Alice can say, you know what, you actually measure my state in this particular basis that will destroy the state and send me the measurement outcome. And now Alice can verify it efficiently using her secret key. And once she is convinced, after this verification passes, now she can send this ice cream popsicle to Bob. So this is basically what the setting is. And this has been studied in the literature for various quantum cryptographic primitives, from classically verifiable quantum money to tokens for digital signatures or tokens for MAC. So all these constructions that we have for such primitives do satisfy proof of destruction, but they're based on these BB84 or subspace states, or what we call coset states. So they're kind of, you can think of it in three categories of states. But all these kind of states are highly structured, so you can actually distinguish them from random. Because ideally, for a pseudorandom state, you would like to have as less structure as possible, so that it's not so that you cannot detect it and distinguish it from random. Okay. On the other hand, we have the pseudorandom state construction, like the random phase state construction, and these constructions are proven to be pseudorandom, but they do not have any inherent structure, so that we can do proof of destruction. Okay, and what we managed to do is that we construct this random phase state, but now on a hidden set. I'll go into more detail later. But this achieves both pseudo-randomness and proof of destruction. Okay. Now, let's look into the formal definition. So again, so now we are just adding proof of destruction to the pseudo-random object. So we have pseudo-random states, PRS. Now we have proof of destruction. So it's PRS PD. Okay. And now we can, so what is the PRS PD? It's again some key space, 0.1 per lambda, which is associated with now 3 efficient algorithms instead of just one that we saw earlier for PRS. So of course, we have the generation algorithm that takes a key k and generates a n-qubit pure state psi k. We have a destruction algorithm that takes an n-qubit state psi k and produces a proof of destruction, so a classical proof P. And then we have the verification algorithm that takes the secret key and an alleged proof and verifies its authenticity. Okay, and the correctness basically says that if you sample a key at random and use it to generate a pseudo-random state psi k and you destroy it to get some proof P, then it will pass verification. Okay, and what does security say? So the first guarantee that we need is the pseudo-randomness itself. So here you should think of the PRS PD as just a PRS, as just a pseudo-random state without the destruct and deletion algorithm, the destruct and verification algorithm. And then you would like it to have the same pseudo-randomness condition that we saw earlier for PRS. Okay. Then the next security guarantee that we need is the unforgeability of proofs. So what is that? So this can be expressed as the following unforgeability game, where you have, so the adversary gets access to, let's say, t many pseudo-random states psi k. So the challenger samples a key at random and gives t copies of psi k. And then the adversary receives the psi k tensor t and also has access to the verification oracle. And now his goal is to generate t plus 1 distinct proofs such that all of them pass verification. And we say that this family of states is unforgeable if there is no QPT adversary who can win this game except with negligible probability. Okay. Now let's look into the construction. So let's have a quick recap of the random phase state construction by Ji Liu and Song, later simplified by Bekersky and Shmuley. So if you look at this construction, it uses a PRF family, and then the key space for this pseudo-random state is also the same key space for the pseudo-random function family. And now the state basically looks like this. So it's for every key, you just have this uniform superposition over all elements in Boolean hypercube, but with this random phase that this function fk decides. Okay. Now, what we would like to have for proof of destruction is to sparsify this construction. So now we would like to think with the same random phase state construction, but supported over a smaller set. So we would like the uniform superposition to be over a pseudo-random set of size 2 to the n by 2. And and 2 to the n by 2, we should think of it as something super polynomial that is still asymptotically smaller than the total size of the Boolean hypercube. And then we would like the same random phases as before. Okay. Now the question is, how do we actually implement this pseudo-random set? The way we do it by using a pseudo-random permutation family. So we start with this fixed string, which is this set of all n bit strings with this prefix, and then we apply a random permutation PR, and we get some state SR. Now, since this permutation was chosen uniformly at random from the PRP family, then this set SR must be pseudo-random. And therefore, that's how we achieve this pseudo-random set of size 2 to the n by 2. And hence, now the key space is basically set of all keys, which is a tuple of a PRF key and a PRP key. And the destruction algorithm is very simply just to measure it in the computational basis. And the verification would be just to check membership in this set SR that we saw earlier. So is the construction clear? Okay, so now let's look why this should be secure. So actually, so what we did is that we have this technical lemma that holds true for a construction, using which you can argue both pseudo-randomness and unforgeability of proofs. So it basically says that an adversary cannot distinguish between these two experiments, meaning its output is identical in both the cases, up to negligible distance, of course. So the first experiment, the challenges the samples a key k, produces this state psi k using the generation, and gives t copies of psi k to the adversary, as well as access to the verification oracle. And then in the other case, the challenger just samples t uniformly random n-bit strings, x1 till xt, and creates this state sim x, which is basically symmetrizing it over all permutations of t items. So you permute x1 till xt in arbitrary manner, and you take superposition of all of them. This state is a symmetric state, meaning that if you permute any of those n qubit registers, the state remains the same. And if you might have seen this earlier, like this is exactly like simulating t copies of hard random state, because a t copies of hard random state could be seen as a uniform mixture of these sim x. And now in this game, what you do is give this sim x instead of the psi k tensor t as in the previous experiment, and instead of giving access to the verification, you give access to the membership to x1 till xt. And okay, so this is basically the two experiments, and it turns out that for our construction, they are indistinguishable. Now, why is this useful? Because now what you can do is that this left-hand side appears in some form or the other in both these security games, and you can now replace it with the experiment on the right-hand side, and then argue security quite in a straightforward manner. Okay, now I would like to mention that so far we just talked about pseudo-random states with proof of destruction, but this definition can also be generalized to pseudo-random function-like states. So you can also associate proof of destruction to pseudo-random function-like states, and this is what we call PRFS PD. And the same construction can also be generalized to give you actually a PRFS PD. So what we conclude is that one function suffices for both PRS PD and PRFS PD. Okay, now I would like to go into the applications. So we know. What we know that is that pseudo-random states and pseudo-random function-like states imply a bunch of these mini-crypt primitives, classical mini-crypt primitives that we saw earlier in the earlier talks. And but a point to be noted here is that all these primitives require quantum communication, and the question is, are they really necessary? So what we managed to show is that you can dequantize these applications in the sense of communication. So you don't need quantum communication. All you need is just classical communication, as long as you're using proof of destruction with your pseudo-random object. And this was also studied using other extensions of pseudo-random states, such as the sort output PRS. Okay. And okay, but really, what we said so far is that we can construct pseudo-random state and pseudo-random function-like state from one functions, and we can construct bit like all these cryptographic primitives from the corresponding pseudo-random object. But really, what is it saying new? Because we already know how to construct all of them from one functions, right? But this is exactly what William talked about, that this matters, or this is interesting, because we know that pseudo-random states and pseudo-random function-like states are somewhat weaker than one functions, at least in the black box setting, or in the relativistic setting. And therefore, all these primitives are also weaker in that same sense. But again, these primitives, when we talk about, we're actually talking about the versions of them where they are allowed to have quantum communication. Can we say something interesting when we restrict them to just having classical communication? Well, you can think of, again, the proof of destruction, like the pseudo-random objects with proof of destruction, and you can say, oh, you get all these applications with classical communication, so does this say something interesting? So unfortunately, this is not enough, because we don't know if pseudo-random states or pseudo-random function-like states with proof of destruction are weak or not from one-way function. So we don't know the exact relationship there. So hence, we don't know the exact relationship when we restrict all these primitives to classical communication. Okay, so far we saw two extensions of pseudo-random states and all the relations to all these primitives in the right. But the overall picture is actually even more complicated. It's really messy at this point. But the reason behind this is because there's a lot of unknown, like there's a lot of open questions here which we don't know. Like, what is the relation between many of them? We really don't know. And so the question is whether we can simplify this. So one of the questions that interests this work would be to understanding the relation between one-way functions and the PRS PD or PRFS PD just like in the same sense as we know for PRS and PRFS and one-way functions. We know we can construct them from one-way functions, and there is somewhat a relativistic separation on the other way. But we don't know if such a separation exists for proof of destruction. And such a separation would essentially mean that all these cryptographic primitives, even when restricted to classical communication, do not need one-way functions. Okay, and a related question would also be to separate other pseudo-random state primitives that give such classical communication application, and one of them is like short output pseudo-random state. Okay, now so how much time do I have? Okay, so now I would like to spend the next couple of slides to explaining how do we get these applications, what is this template. So it turns out that there's a nice technique which you can use to just make these things classical. Okay, so usually in all these applications, the source of quantum communication is that like we have two parties, Alice and Bob, and they need to exchange some pseudo-random state or pseudo-random function-like state. For concreteness, let's take the example of the MAC scheme or the message authentication code scheme, which uses a PRFS family. So here the key space for the MAC scheme is the same as the PRFS. So you share a secret key, and then when Alice is trying to send a message M and its signature and its tag, then what she basically does is that she takes this message and does the PRFS generation to get this psi k comma m and sends this to Bob. Bob can then use this k and m to generate the PRFS state corresponding to it and check if they are similar. Now, this is a very crude way of verification. Of course, you can make it much better. But the point is, this is what the scheme on a high level looks like. And you see the quantum communication part is because of this psi km. So what we can do with proof of destruction is that we can make this classical by just doing the same process, but now Alice will not send the state itself as the tag, but she would destroy it using the destruct algorithm and send the proof of destruction. And once she sends it, Bob can now then verify using his secret key by just running the PRFSPD verification. So this template actually works in most, but not in all cases. Okay, so that's all I wanted to say. But since I have 2 minutes, I can show that where this actually fails. So it fails in this example to one-time signatures. So for one-time signatures, classically we know how to construct them from one-way functions, and the idea is we just exploit the one-wayness of this function. Meaning, so what is one-wayness? Just brief recap. So if Alice gives k uniformly if Alice takes k uniformly at random, generates the one-way function on it, and sends this y to the adversary, then the adversary cannot come up with a pre-image of y. Now, it turns out you can exploit this property to construct one-time signatures, meaning the signatures you can use it just for one time. If you use multiple times, it won't be secure. And the public keys for such signature scheme that we can construct from one-way functions are actually just the one-way function images, so a bunch of y's basically. And in the quantum setting, Morima and Yamakawa they observe that such one-wayness also holds for the pseudo-random generator. And therefore, you can use the pseudo-random states like psi k as the public key and get a one-time signature scheme. So now the problem is that we have these quantum public keys, which are basically the pseudo-random states. So if you want to use the same template as we saw before to dequantize it, we can say, okay, now we don't want to look at the pseudo-random state. Let's look at the proof of destruction of it. So you want to argue, is there a one-wayness property for the pseudo-randomness? So if you consider this map from k to pk, is this pseudo-random? Turns out this is not really true, because all these two properties, pseudo-randomness and unforgeability, are not enough to ensure this. Indeed, you can always add a dummy key to your set of keys, and which accepts verification on all proofs, and this would indeed be this would indeed not affect the pseudo-randomness or unforgeability, because it's just adding one key, so with high probability we'll never actually sample it. But now this adversary can always output k tilde as this k prime as the pre-image and break the one-wayness. But the conclusion is proofs of destructions are not one-way, so we cannot just use this template. And the way we fix this is by actually changing the verification algorithm for the signature scheme itself to rule out these indemnities. And yeah, and I would like to conclude with that.
Thank you, Amit. Questions?
I'm a bit confused. So you said that one-way functions imply.
Wait, where exactly?
Here. Yeah.
Sorry.
So you said that one-way functions imply pseudorandom states with proofs of destruction, but didn't your construction involve pseudorandom permutations as well?
Yeah. So we can. So okay. So first of all, there's also like you can also do this by just pseudorandom functions, but you can construct both pseudorandom permutations and pseudorandom functions from one-way functions, because you can just take the pseudorandom function construction and do these shuffling kind of constructions to get yeah. Phi still I'm not sure, but I think there's been improvements to them. Like there have been like these compilers have been generically studied for the quantum setting, and they work out. So if you actually start with something random, which satisfies like oracle based pseudo randomness, then you can actually get oracle based pseudo randomness, but with a permutation.
I mean, does it not have to be like a perfect permutation? Like,
so we will get a permutation. Like this compiler does give you a permutation.
Okay.
Other questions?
Thank you. So the construction you showed for the PRFS with proof of destruction, it looks quite similar to the one in the pseudo entanglement work, right?
Yeah, yeah.
Yeah. So does that construction also give you basically the same thing, or am I missing something?
So I don't know completely, but I think they have a few construction in that paper, and one of them does look like this, and I think it also has the properties that they study in the pseudo entanglement paper. Yeah.
Okay. Thanks.
Hi, thank you for the talk. I was wondering, so as you mentioned in the beginning of the talk that there's proof of destructions before on PB84 states and COSET states, and those usually kind of use the structure that's inherent to them to kind of show that you can make compatible measurements, but you can show that you can do it structurelessly. Was there a sort of relation between these two that maybe you can, I guess, find a more intuitive reason for what the proofs of destruction are based off, like a different property than the entropic relations between these sets of sets?
You're saying, can we abstractify what we need to have this proof of destruction from it?
Yeah.
To be honest, like the only way I imagine it, like only way I know of constructing proof of destruction is where you have some like again, I would like to say hidden structure, like for example, coset states or like subspace states. They have a hidden structure in the sense that when you measure it, you can verify it. So the problem is verification. So you need some structure to verify it. So if it's like a subspace state, you can verify using the membership oracles. Now we are kind of doing it using the subset membership oracle. I really don't know of any other way to do this, but again, like I don't have any like impossibility result as such, right? So I don't know if that answers.
So I think classical channel commitment or classical channel primitive was already constructed by Anand's Kian UN paper by using tomography.
Yeah.
And how is different from your?
So okay, that's a good question. So yeah, okay. So this is right. So talking about this commitment scheme, right? So yeah, it's different from their constructions in the sense that we're actually following basically Nau's commitment scheme. Like it's basically following Nau's commitment scheme, but now you use a pseudo random state. pseudorandom state with proof of destruction. So in some sense, like when you destroy the pseudorandom state, you get something. You get something proof of destruction which have this structure that you can use to have now commitment scheme. But like there is actually an additional assumption that we make on our pseudorandom state with proof of destruction. This is basically a pseudorandomness on the proofs itself. So the way we prove it is we use this additional property and then we use the pseudorandomness to just follow the same proof technique as the now bit commitment has.
And so your, for example, your commitment from PRSPD is some commitment with certified deletion.
Can you repeat the question?
So if you construct bit commitment from PRSPD,
Yeah.
Does it commitment with certified deletion or just normal commitment? So because your PRSPD has some type of certified deletion.
Yeah. So I'm not sure what you mean by bit commitment with certified deletion, but
yeah, just you can delete committed data and you can show that this.
Yeah, but we are all the communications here are just classical, so there is no quantum state that you are giving to.
But maybe you can use quantum channel.
Yeah, if you use quantum channel, yeah, then okay. So we are trying to make it somewhat in between quantum and classical. Is that what you were trying to say?
Yeah,
like you send a quantum state, but now maybe while revealing, just using quantum classical communication.
Yeah, so just if you directly use this your PRSPD to construct quantum commitment, is this automatically be some commitment with certified deletion?
I'm not sure I understand that question because the commitment scheme we have is completely classical in terms of the communication. So there is never the case that that Alice would be sending Bob something quantum that you can do certified deletion on.
Maybe we can discuss later.
Sure,
but just from PRSG you can construct commitment. I mean, so just if you have one PRSG, you can construct a quantum commitment by using Yan's canonical form. And in that case, your commitment is automatically PRS with proof of destruction.
Oh, okay. Maybe we can talk about this.
Okay, let's take any remaining questions offline and thank Amit.